very much. Yeah, first of all, again, thank you so much for the opportunity to speak. This is my first proper maths conference speaking. Yeah, this is definitely a new experience for me. So thanks for your patience in advance. Yeah, so today I want to talk about transitive subgroups of the holomorph and Hopf-Galois structures on separable field extensions, which are objects not, well, they're related in some sense to skew braces and stuff like that. But yeah, they're sort of a different object that I want to look at today. So I'll start with something that probably most of you know much better than me, and that's looking at skew braces and how they relate to the holomorph. So let's start with a group B plus. I'm gonna note, well, I've notated it different to how Lorenzo notated it. I think he put a dot there instead of a plus. This plus doesn't mean it's abelian, as I'm sure most of you know, but I think it's there for historical reasons. So yeah, let B plus be a group, not necessarily abelian, and we say that B plus circle is a skew brace if two things hold. One, B circle is a group, and this sort of distributivity operation holds. Again, I've sort of written it in more additive notation, but yeah, it's not necessarily abelian. Okay, and if we define, if we have a circle operation and define lambda sub a of b to be this, then we see that actually lambda is a group homomorphism between B circle and the automorphism group B plus, given by this correspondence here, and sort of getting it back from our lambda a, we see that we can write the circle operation as a sort of a composition of two operations, the lambda a and this LA, which is the left translation map. So yeah, B just goes to A plus B. Just paying close attention to this for a second, we see that actually the left, the set of left translations is it's normalized by the automorphisms of B plus. So yeah, I can conjugate it by any automorphism, and I get back another left translation. And so because of this, I can define this sort of weird product thing, which is the semi-direct product of the set of left translations and the automorphism group. And this we call the holomorph. And you can view this as a subgroup of the permutation. And yeah, so there's a bit of a weird product. Again, I'm sure you're all familiar with this, so I'll not go into too much detail. But yeah, you have the automorphism group acting sort of non-trivially on the left translation map in sort of this way. And so you can view B circle, group B circle, you can view it as a regular subgroup of the holomorph via this correspondence. And as Lorenzo mentioned in his talk, we get a correspondence here, right? We have operation circle such that B plus circle is a skew brace. They're in bijective correspondence with regular subgroups of the holomorph. Yeah, I think he characterized regular subgroups. And one way, a way I like to see it is that sort of the same cardinality. Well, I guess in this case, Jesus has the same cardinality as N, and sort of G acts transitively on Hol N. So yeah, okay. So that's the picture from the skew braces side. Okay, so I want to look at now, I want to turn your attention to these things called Hopf-Galois strictures. And so let L over K be a field extension, a Galois field extension of finite degree. Let's say G is the Galois group. Then the group algebra KG acts on L in such a way that it induces this isomorphism. So yeah, L is a module over KG, and blah blah blah. And basically, KG is an example of a Hopf algebra. In particular, well, in this case, it's a co-commutative Hopf algebra, and it acts on L, like I said. And yeah, so we ask a question mathematicians usually like asking, and we say, are there any other structures acting on L in a similar way? So are there any other co-commutative Hopf algebras acting on L such that you get this, well, it sort of induces some isomorphism between these two groups. And it turns out, yes, there are in a good number of cases. Sometimes there aren't, but we call this structure, we call it a Hopf-Galois structure. And yeah, a Hopf algebra is kind of like sort of you can sort of view it as a sort of a K algebra, and then you can sort of dualize it to be a K co-algebra, and then it sort of has a sort of an additional map. So there's a lot of structure going on, but I'm not going to go into too much detail surrounding that. And yeah, so basically we turn our attention to finding Hopf-Galois structures, looking at them, looking at the way they behave, and yeah, just having some fun with them, really. And a big theorem that really helped the categorization of these was a theorem by Greuter and Pargas in 1989, and they showed that Hopf-Galois structures on L over K correspond bijectively to regular subgroups N in perm G, normalized by the image of the left translation map. And then you have, so the Hopf algebras are given by this. So yeah, G acts on N by conjugation by the left translations, L on automorphisms, and H acts on L by this thing called Galois descent, which is something that I won't get into massive detail with. But basically, this gives a picture from the Hopf-Galois structure side. We have they're bijective correspondence with regular subgroups of well, at the moment we've got in perm G, but if I go into the next slide, in 1996, Bayet gave a correspondence between such a situation and so regular subgroups G of Hol N and Hopf-Galois structures. And I guess one thing that this was really cool about it was the fact that well, at one point we were looking at subgroups of perm G, and now we're just looking at subgroups of the holomorph, which is in general a much smaller group, so it's a lot easier to work with. another thing is that this connects it to now skew braces, right? So we have a correspondence between skew braces, Hopf-Galois structures, and regular subgroups of the holomorph. This is really, really interesting now, because it means that we can take results sort of made discovered with skew braces, and we can pull this across the correspondence, and we can sort of have a look to see what that does for Hopf-Galois structures and vice versa. So an example of this was Aldelli and Byatt in 2019. They gave results on skew braces of square free order, and this is sort of on the back of their work on Hopf-Galois structures on Galois extensions of square free degree. So this is really tangible. It's really powerful stuff, and yeah, I find it quite cool. However, greater progress theory and Byatt's correspondence also both apply to not just Galois extensions, but the theory works more generally, and they apply to separable extensions. So the extensions don't have to be normal. So what does that situation look now? Okay, so let L over K be now a separable extension of degree n. Let E be its Galois closure, G be the Galois group of E over K, G prime the Galois group of E over L, and X be this quotient group. Well, now we have that for each regular subgroup n of perm X, normalized by the image of the left translation map now to perm X, we have a correspondence. So now instead of instead of L here, we have E, and yeah, G acts in sort of the same way and stuff. And this gives a Hopf-Galois structure on L over K. And looking at this through Byatt's translation, we now look at transitive subgroups G of hol n instead of regular. So what does that mean? So n is the same size as X, which is the same size as the degrees of the field extension. But G, although it's a permutation group of degree n, remember we're still embedding it as a subgroup of hol n, right? It's no longer required to be of order n. And this is a big thing, because we can have control, I guess, over the size of n and kind of the behavior of n as a group, but we've kind of lost a lot of control over G, and that sort of makes things a bit more complicated and confusing. But yeah, I guess the question is, can we do things with that? And so what I want to do for the rest of this talk is talk about transitive subgroups of hol n, and looking at Hopf-Galois structures on separable extensions instead of Galois. So yeah, sort of moving away from its connection with skew braces, but I don't know, there could be a connection there, but anyway, I'll talk about that. Okay, so first some relevant results. Results on separable extensions. We've got so Cole gave some results on separable degree P to the R extensions and degree PM separable extensions where M and P are co-prime, so P is prime in this case. Crespo, Riambella gave results on induced Hopf-Galois structures. Crespo and Salguero gave results on separable degree P squared and 2P extensions. Aldelli and Byatt gave a sort of a full classification of results on square-free Galois extensions, and in a sort of an initial attempt to generalize this theory, well, on the square-free work, Byatt and Martin Lyons gave separable results on separable degree PQ extensions, where P is equal to 2Q plus 1. So Q is a Sophie Germain prime, and P is a safe prime. And so it's this work that I kind of want to have a bit more of a look at, and this work that I've tried to sort of see if I can generalize a bit further. So let's just have a look at what they did. So their strategy was to look at the different abstract groups N, find all transitive subgroups G of Hol N, and determine when two of these groups, G1 and G2, which arise from or give rise to Hopf-Galois structures, maybe of different types, N1 and N2, are isomorphic. And if they're isomorphic, then what we have is G1 being isomorphic to G2 gives rise to a Hopf-Galois structure of both types, N1 and N2. Oh, what I probably should mention, I realized I didn't mention, is that if G is a transitive subgroup of Hol N, then, and we get the Hopf-Galois structure, then we say that it has a Hopf-Galois structure of type N. So that's where this type is coming from. So yeah, I want to first give an example from their Sophie Germain work. Okay, so a group of order PQ is either cyclic or Machiavellian. So yeah, CP semi-direct product CQ. So I guess like a dihedral group or something like that. We let N be the cyclic group of order PQ, and we can work with this presentation. And then we can decompose the holomorph into these factors. And because of the fact that P is equal to 2Q plus 1, we see that it has order 2TR plus 1 times S times PQ squared. So where P minus 1 is 2Q and Q minus 1 is 2 to the R times S, where S is odd. And we can generate these automorphism groups with some automorphisms alpha and beta and gamma and delta. And sort of initial looking at this, we can see that N is transitive on Hol N, it's actually regular on Hol N, and N is normal in any subgroup of N, and so we can extend N by any of these subgroups. Yeah, we can extend N by any subgroup of Ort N, and we can still get a transitive subgroup. And this is their cyclic results, or part of it, should I say. And so this table gives all the transitive subgroups of Hol N where N is cyclic. And you can see these first 6 cases are N extended by different subgroups of Hol N, of Ort N. And then looking at it a bit more, we get other groups arising, these J sub T, which actually, if you sort of stared at it for a bit longer, this is the Machiavellian group order PQ. And that, yeah, so that's also transitive in this case. Okay, so this is just looking at the cyclic case. They also did work on the, yeah, gave results on the methylene case, but I won't go into detail with that. So, like I said, I was wondering if it was possible to generalize this. The big problem is that when you look at, well, if I go back, when you look at the order of whole n, we get this p-1 and q-1. Right, so we can control the order of n, so in this case pq, right? But the order of ort n, well, when n is cyclic, p-1, q-1, and in the subfeature main case, they factor sufficiently nicely that we don't get too many primes appearing that we kind of don't have much control over. In sort of more general case, we get loads of primes arising, and it, yeah, and so this is because subgroups of whole n will have ordered dividing, well, p-1, q-1, pq, when n is cyclic, and so it will have orders relating to these primes, and yeah. So the question is it feasible? So an initial observation is that, so let p and q be distinct odd primes. For p not congruent to 1 mod q, we actually just get one Hopf-Galois structure. And this result was shown by N96 in the same paper that he gave the correspondence between the regular subgroups of the holomorph or transitive subgroups. So let's assume that p is just congruent to 1 mod q, and so we can factor them like this. We can assume this for the factorization. And again, we get that for n cyclic of order pq, what n is generated by these alpha I, and beta I, and we can, yeah, so we can factor all n into this product of groups. So much of the theory sort of still applies, but the tricky thing is now is actually looking at subgroups of each of these factors, and it doesn't look the nicest, but yeah, it turns out that it is possible to obtain all the subgroups of each factor, alpha I, beta I, and this is kind of what they look like. Again, a bit icky, but it's possible. Yeah. And so, like I said, the similar logic applies. So n is regular. We can in whole n we can extend it by any subgroup, blah blah blah, and so that's the sort of the logic behind this first set of groups. And then I didn't say much about it, but you get these JT appearing as well, and you can extend them by any subgroup of the automorphism groups, group generated by the alpha I's. And JT C0 is just this. So yeah, and so yeah, it turns out that you can do this, which is quite nice, and you get a formula for the isomorphism, the number of isomorphism types of permutation groups G of degree PQ, which are realized by Hopf-Galois structures, a Hopf-Galois structure is cyclic type. And yeah, I'll just sort of explain what the sigma I is. It turns out that these are quite difficult to count, and yeah. Okay, so and then a bit of a remark here. if we do specialize this back to the Sophie Germain case, then here E0 is 1, L1 is 2, V1 is 1, F1 is R, S is this product, and EI is 0 for I between 2 and n. Then we actually get back the result of Myers in this case. So there are this many isomorphism types of permutation groups G, degree PQ, where P is 2Q plus 1, which are realized by a Hopf-Galois structure cyclic type. So it's quite nice that works. It's reassuring that it works. I'd be worried if it didn't. Okay, and it turns out that you can sort of do similar work on the Mesabelian case. So I didn't include their Mesabelian results, but I just thought I'd briefly include my Mesabelian results. And again, it specializes to the Sophie Germain case, which is quite nice. So it turns out it's very possible, very feasible to do this. Okay, this is all well and good, but we have other questions to think about now. So L over K is only 1 degree PQ intermediate field between E and K. So I guess a reasonable question would be to ask, well, how do the other degree PQ fields, intermediate fields, behave, right? So we can focus on L over K and say stuff about that, but can we say something about these other fields popping up? Well, there may be Hopf-Galois structures on L over K. I should mention that we're only exploring ones here where Hopf-Galois structures do pop up, right? We're doing it the other way around. We're sort of finding the case where Hopf-Galois structures pop up, and then we're relating that back to a field. That's kind of what we're doing. So we only see Hopf-Galois structures popping up, but it may be the case that some of these other fields don't have Hopf-Galois structures on them. And so it would be interesting to investigate these. And so I'll just say a bit about this. Okay, so recall our G and G prime. Well, we can consider the pair G prime, and here G prime is a subgroup of index n and has trivial core. What do I mean? Well, the intersection of all its conjugates just is trivial. And we work with the index PQ subgroups H of G, such that F is this, right? So I want to draw your attention to the fact that this is now no longer a Hopf algebra. So please pardon my abusive notation here. H is no longer a Hopf algebra. It's now a subgroup, an index PQ subgroup of these groups G. So these are the groups G here. And so there are a number of possibilities. Okay, so one possibility is that H is conjugate to G prime, and so F and L are a conjugate field, and so they'll behave in more or less the same way. So F will have Hopf-Galois structures on it, and and so there's the same Hopf-Galois structures on it. Another possibility is that H is not conjugate to G prime, but there is some phi in ORT G with phi G prime equal to H. That's one possibility. G prime. Another possibility is that G prime and H lie in separate ORT G orbits, but the core of H is trivial. So from this, H and G prime may or may not be isomorphic as abstract groups, and F may or may not admit a Hopf-Galois structure. If it does, then this pair GH now will show up as a transitive subgroup of whole n for some n of order n. So yeah, so in this case, basically, if we find an index PQ subgroup with trivial core, then well, if it shows up in either this table or one of these, then it leads to a Hopf-Galois structure. If it doesn't, then F doesn't admit a Hopf-Galois structure, right? And then the final case is that G prime and H lie in separate G orbits, and its core isn't trivial, and so F would have a smaller normal closure, yielding now this permutation group. And so we again ask ourselves if this corresponds to a transitive group of whole n. So what we do is we compute the core of H, we take the quotient of G by this core, and again ask ourselves, does this is this realized as one of these groups? And if it is, then yeah, again it has a Hopf-Galois structure. If it isn't, then it does not admit a Hopf-Galois structure. So we a strategy for this is computing the index PQ subgroups H of G and categorize them in terms of conjugacy class, orbits under Alt G, and abstract isomorphism classes. And we also need to compute the core, and then we take G mod C, G quotient out C to see if it appears in the list of transitive subgroup. And a big result is that for n product of two primes, we actually find that all intermediate field extinctions admit at least one Hopf-Galois structure, which is, yeah, this is not an obvious result. It's possible that sort of smaller field, smaller, in the small case or small product of prime case, I guess, cases that all such fields will admit Hopf-Galois structures, but maybe as n becomes more complicated, then we may find an example of that not to be the case. But at least for PQ, we find that all intermediate field extensions admit at least one Hopf-Galois structure, which is pretty cool. So one thing to note is that for P equals 2Q plus 1, it's feasible to compute everything very explicitly. However, making use of the generalization of Hopf-Galois theorems, we can approach the problem very efficiently, even for general PQ. So generalization of Hopf-Galois theorems being Hall's theorem, which, I hadn't come across before I sort of started looking at this, but I assume most of you will probably know what it is. Okay, so in short, the work can be summarized in these tables. So we have some tables there, which I won't go into much detail because probably doesn't add too much. But one thing that's interesting is that there is a pattern in the tables. It looks like the group's divisible by the same powers of P and Q behave pretty much the same regardless of the other factors co-primes P and Q. So Hall's theorem tells us why this is the case for conjugacy classes. It can be proved that this is the case for the Alt G orbits, the general PQ case, but it looks like the arguments are more general square free n. The arguments might be a bit more subtle. I haven't sort of fully wrapped my finger around that yet. But it's looking like the case anyway. It may also be the case that for more general square free n, we find intermediate fields which don't admit Hopf-Galois structures. Well, I've already mentioned this. So as a kind of last thing, although I think I want to give a couple of remarks at the end, I'll sort of outline possible questions and sort of future goals. So investigate whether the Hopf-G orbits depend on factors co-primes T and Q. So this actually was done. It's true for both of these cases. And are the Hopf-G orbits independent factors co-prime for general square free n? A next step, a possible next step from the PQ work would be investigating separable degree PQR extensions, where PQR are general or primes. I found that it was a nice way to go from the Sophie Germain case and the PQ case and sort of generalize that to PQ. So maybe this is a way to go about it for the PQR case. And so you have this sort of relation between these primes. And again, sort of what happens in degree sub-extensions and sort of the same questions, but for sort of more general square free n. It turns out that if you have this sort of relation between the primes, this is called the Cunningham chain. And so maybe Cunningham chains are a way to approach this more generally. I'm not sure, but it's a possibility. So yeah, I'm coming to the end of my talk, but yeah, I think one question that I've been asked before is why the focus on square free extensions, and the answer to that is that well, we have a classification for groups of square free order, and so remember me saying you can sort of control. We can control the behavior of n, big N, capital N, but we can't necessarily control the behavior of the transitive subgroups. So yeah, it's basically just one way to control it, to get something that is sort of feasible to write down. But yeah, yeah, there's, apart from that, there's no particular reason why square free n. It could lead to sort of a nice answer. And yeah, I think I'll end it there. I think I'm just coming to 40 minutes. So yeah, thanks very much.